Hi students, Professor Gray here. We need to talk about density, which is the ratio of the mass of an object to its volume. So we've got density is equal to mass divided by volume. And the unit for this is grams divided by centimeters cubed, remembering that centimeters cubed is exactly the same as milliliters and is exactly the same as a cubic centimeter. And you can see that down here on the bottom when we look at the density of three different substances. So the first substance we have is mercury, which is our liquid metal, and it has a very high density. So it's 13.6 grams per centimeter cubed. And then we have water in the middle, and water has a super easy density. If there's any density that you need to memorize, it's water. Water has a density of 1 gram per milliliter. And again, you could say 1 gram per centimeter cubed, or you could say 1 gram per cc. Now, copper is our metal over there in the little balls, and it has a density of 8.94 grams per cc, or grams per milliliter, or grams per centimeter cubed. You could also write the density of something as grams over the volume like this, and you can also put a 1 on the bottom. That is saying exactly the same thing as this. It's just writing it in a different way. If we put all three of those substances together, we could see that the most dense substance, mercury, would be on the bottom, and then we'd have copper and we'd have water on the top. Now that's only going to work if you have three substances that are insoluble in each other, okay, that aren't dissolving each other, but that works that way for those three insoluble substances. Okay, so let's do some problems. So number one says, what's the density of a 2.5 liter container of vegetable oil that has a mass of 2,459 grams? Well, when we're figuring out the density, we're going to need the equation for density. So density is equal to mass divided by volume. And remember, we want that in grams per milliliter, or cubic centimeter, or centimeter cubed, either way. And if we want to rewrite that with letters, we'd get D equals M over V. Sometimes you'll see the D as a big D. That works too. We can also do the density triangle. So what we'd do is we'd put the density down there, the M up here, and the V there. And we'll get back to using that in a little bit. Or if you like cute things, you can do the density ladybug. So the density ladybug looks the same as the density triangle, the density pyramid. There you go, right there. Okay, so let's write out the variables that we have. So the mass, that's equal to 2,459 grams, and the volume is equal to 2.50 liters. But we know that we need to have our volume in milliliters, so we need to change the liters to milliliters, and we're getting pretty good at that at this point. So we want to get rid of liters. So are we going to put it in the top or the bottom of the conversion factor? We're going to put it in the bottom because we want to have liters divided by liters, which is equal to what? 1, because anything divided by itself is equal to 1. And the unit that we want to go to, we're going to put that in the top, in the numerator. Now, which unit, milliliters or liters, is the bigger one? liters. So we're going to put the 1 next to liters and figure out how many milliliters we can cram into a liter. Well, this is one of those ones that you should know by now, and if you don't, just pull out a chart and it'll tell you that there's 1,000 milliliters per every 1 liter. So the liters cancel out and we do the multiplication on that, and what we're gonna get is 2,500 milliliters. Now in this one, I want you guys to keep in mind that there are 3 significant figures here. So in the 2,500, those first 3 digits are significant, and the 0 on the right hand side in the ones column, that's just a placeholder. So that first 0 is significant. Okay, so we have the mass and we have the volume, so we can just plug and chug. We can say D equals M over V, and that is 2,459 grams divided by 2,500 milliliters, and still keeping in mind that we've got 4 sig figs here and 3 sig figs here because of what we just said right here. This original one had 3 sig figs, and so our answer is going to have how many sig figs? 3, that's right, we go with the lower number. So what we get for this is 0.9836 grams per milliliter, and we put that extra digit there, that 6, to tell us whether we're going to round our third significant digit up or keep it at 3, and 6 makes it round up. So our final answer is going to be 0.9836 grams per milliliter. We could also write this as 0.983, excuse me, bad teacher, bad. What on earth was I doing there? I was just rewriting. I was just going on autopilot. 0.984, 3 sig figs, 0.984 grams per milliliter. And the other way that we could write this is 0.984 grams, and you can put that over 1 milliliter, or you could just put per milliliter, or you could write it as 0.984 grams per milliliter, like that. There's a bunch of different ways you can write it. They're all the same. Now, if we were to use the density triangle or ladybug, which we really don't need in this problem, but we might need in problem 3, is this. You're solving for density. So if you have the density triangle, whatever you're solving for, you put your finger over that. And that'll tell you that density equals mass divided by volume. Now, if you wanted to solve for volume, what you would do is put your finger over the V here, and you would see that V is equal to mass over density. Okay, so that's how that works. All right, so number 2 says let's calculate the density of the rock in the picture to the right. The rock has a mass of 29.5 grams. So again, we're doing density, and density is mass over volume. So we want to go ahead and list the variables that we do have. So do we have mass? Yes, it's 29.5 grams. Do we have volume? No, we don't at this point, but the way that we can find it is over here. We can do something called volume displacement. And so the V of the rock is equal to the volume of the water final, which would be this right here, minus the volume of the water initial, and V initial is right there. Okay, so we take the bigger number minus the smaller number. So the volume here would be V final, and if we read this, the bottom of this meniscus right here, it would be 20.0 or 20.1. Remember that last column right there is where we have some wiggle room. So maybe I look at it and I say, okay, the bottom of the meniscus looks like it's hitting on exactly 20.0. And you say, oh, no. It's definitely 20, but it looks like 20.1 to me. Is that okay? Yes, because the last digit is where the guess is. And so right here, that's 20. And right there is 21. And remember, we need to make a guess. So if I guessed 20, just to make it easy here, it would be 20 milliliters minus whatever the initial water volume was before we dropped the rock in. And it looks like the meniscus is a little tiny bit below 7. So the 5 right there is this big graduation here. And then that's 6. And then the next one up here is 7. So maybe I call that 6.9 milliliters. Now, would that be okay if you thought it was 6.8? Yes, because the 6 is certain, but whatever is behind the decimal, that's where we've got some wiggle room. So we do 20.0 minus 6.9, and using the rules for addition and subtraction for sig figs, we are going to finish our answer in the tenths column, because this goes to the tenths and that goes to the tenths, and that gives us 13.1 milliliters. So now we can just plug and chug. Now we can do the density is equal to the mass divided by the volume. So 29.5 grams divided by 13.1 milliliters, and the numerator has 3 sig figs and the denominator has 3 sig figs, and we end up with an answer that has how many sig figs? 3. So we get 2.25 grams per milliliter. Now the density of water is what? We learned that it is 1. And if the density of rock is 2.25, which is over double the density of water, the picture should make sense because it has the rock sinking. So whenever you're doing a problem, make sure your answer makes sense. All right, so number 3 says, what is the mass of 5.50 milliliters of mercury if mercury has a density of 13.53 grams per milliliter? So again, let's just write out the equation for density. Maybe we make ourselves a density triangle here. And then go ahead and list your variables. Do we have the mass? No, the question is asking for the mass. What is the mass? And volume. Well, milliliters is a unit of volume, so that's going to be our volume. And our density is 13.53 grams per milliliter. Okay, so we have to solve for m, and we can do it a few different ways. What we can do is we can do the magic of algebra, and the magic of algebra says that things can move diagonally across an equal sign all day long, and that's legal. So the v can move diagonally and go visit d up there, And that would give us dv equals m. And if we just want to switch that around to the other orientation because we like the variable that we're solving for to be on the left-hand side, we can do that too. It works just like that. Or we can use the density triangle. So we would cover up m, and then it would show us that m is equal to dv, which is what we did right there. Or you could do the traditional algebra way, which says that if you want to get rid of v and it's in the denominator, you have to multiply by v, but what you do to one side, you have to do to the other. So the v cancels out, and what you get is vd equals m. And VD is exactly the same thing as DV, so we have the same thing as here and here. However you like to do it that gets you to the correct answer is the way that you should do it. However your brain works. Our brains all work differently, and how I solve a problem may not be how you solve a problem, but if you're getting to the right answer, that's good. Okay. So what we have is m is equal to d times v, and the density is 13.53 grams, and this time we're going to put milliliters in the denominator on purpose so we can see what we're going to be canceling out. Again, this is exactly the same as that. It's just two different ways of writing it. And then we're going to have 5.50 milliliters multiplied by that 13.53 grams per milliliter. Now, what cancels out? The milliliters, because you have a milliliters in the numerator and you have a milliliters in the denominator. If you need to write the ones in so you can see that you have denominators there, feel free to do that. Okay, so now we have a unit of grams right there, which is good because we're solving for mass. So again, be checking yourselves along the way to make sure your calculations are making sense. All right, so we have 13.53 times 5.0, and that is going to give us 74.4 grams. And right here I've got three significant digits because 5.50 is 3 sig figs, and 13.53 is how many? 4 sig figs. And we're multiplying those two values together. And when we multiply, we have to follow the multiplication and division rules for significant digits. Alrighty. Number 4. Number 4 says calculate the width of a piece of wood. And the piece of wood is over there to the right, and it gives you the density of the wood. And you're going, wait a minute, I thought density was mass and volume, and now you're asking me for width. What on earth? Well, you can do this problem. So again, let's just go ahead and write the equation for density, just so we get practice with that. And then let's write out the variables that we have. So do we have mass? Yes, we do. 13.56 grams. Do we have volume? No, we don't. Do we have density? Yes, we do. That's 0.53 grams per milliliter. Now, does that density make sense when you think of real life and you know that water has a density of 1 and you know that wood floats? Yes, because if wood's floating, it probably is less dense than water. So, yeah, making sense there. Okay, so again, how are we going to solve for the width? Well, the thing about volume in a rectangular object is something that we have to go back to geometry class for. And the equation for the volume of a rectangular object is length times width times height. So if we can solve for the volume, and then we have the length, and we have the height, and it doesn't matter which we call which, we can solve for the width. So let's go ahead and do this. So we're solving for volume here so we can get to the width. So by the magic of algebra, we can move the volume up here. That's going diagonal across the equal sign. And we can move the density down there, and we get volume equals mass divided by density. And you can write a 1 in the denominator under volume if you need to. Or the other way you guys could have done it was you could use the density triangle, and I just erased my density triangle. Boo! But here it is up here. So you're solving for volume. So that would tell you, if you put your finger over the volume, that volume is equal to mass over density, which we just did right here. Okay, let's plug and chug. So we've got 13.56 grams, and we're going to divide that by 0.53 grams per milliliter. Okay, what cancels out? What do we have that's the same on the top and the bottom? What we have is grams, so we're going to cancel out the grams. And now we have a milliliter that's on the bottom of the bottom. The milliliter is in the denominator of the denominator. And whenever you get something in the denominator of the denominator, it gets a ticket on the train to the top. And I'll show you why this is true in a second, but let's just get to the answer first. So there's a lot of parts to this question. So 13.56, that has how many sig figs? That's got 4 sig figs. And 0.53, how many? 2 sig figs. And we're doing division here, so we follow the multiplication and division rules for sig figs. So our answer should have how many sig figs? Our answer should have 2 sig figs. So we have 25.58 displayed on our calculator, and that would be in milliliters. And then to switch it to the correct number of significant digits, you'd look at the 5 to decide if you round up that first 5 there, and you ignore the 8. You don't round the 5 up and then round the next 5 up. What you would get is 26 milliliters for the volume, okay? So the volume is equal to 26 milliliters. All right, so why does something on the bottom of the bottom get to go to the top? Well, we have to take a detour into some fractions in order to do this, to show you that I know what I'm talking about, okay? So remember complex fractions like this? So you have 4 divided by 3/5, so you have a fraction within a fraction. If you rewrite that as 4 divided by 3/5, remember the way that you solved this was you said, okay, 4, and you multiplied by 3/5 upside down. So you flipped that fraction, and that dot is multiplication in case you haven't seen it. Now look, the 5 got to go in the top there. See? It's up there. So we're multiplying 4 times 5 and divided by 3. It works the same when we have units. So milliliters was in the denominator of the denominator, and it got to go to the top. So that is the reasoning that something in the bottom of the bottom gets to the top. And now forevermore, you're going to believe me, right? Right. Okay, so back to the problem because we haven't answered this yet. So another little thing. We are on the problem of finding the width from the volume. And you might be saying, I have no idea how to get from milliliters to centimeters. Yes, you do. 26 milliliters is the same thing as what? 26 centimeters cubed. Yay, we're not to centimeters yet, but we're at centimeters cubed, and this is fabulous, okay? So our volume is length times width times height. So we have length times width times height is equal to 26 centimeters cubed. That means that the width will be equal to 26 centimeters cubed divided by the length and the height, okay? So then we have 26 centimeters cubed divided by 6.45 centimeters. And on the bottom is also 2.50 centimeters. Again, it does not matter which one of those you call the length and which one of those you call the height. Either way it works, because 3 times 5 is the same as 5 times 3. Okay, so what that gives us is 26 centimeters cubed divided by 16.1 centimeters what? Squared, because when you have exponents and you're multiplying those units, the 1 and the 1 add, which is one of those weird little quirks of math, but that's how it works. And now what we're going to do is we're going to do 26 divided by 16.1, and 26 has 2 sig figs, and 16.1 has 3 sig figs. So how many significant digits will you have in your answer? You will have 2, because those are the rules. So that's going to be 1.6, and we need a unit on this in order to get full credit. And when you have something with an exponent divided by the same thing with another exponent, the division means you subtract. So over here we were multiplying the exponent of 1 times something with an exponent of 1, so we added them. 1 plus 1 is 2. Now we're going to do 3 minus 2 because we're doing division. And 3 minus 2 is what? Is 1. So we have centimeters to the first power, and whenever we have a 1, we don't have to write it. And all of a sudden, aha, the width is equal to 1.6 centimeters. That was a lot. Okay, moving on. Now, most substances, as you heat them up, so see how we're heating up this substance, have a density that decreases. And the reason for that is what happens as a temperature increases is that the volume increases. So if you have a larger number in the denominator, right here, that would be when you're hot. That means that your density value will be less. So if you have a cold situation and you have 3 divided by 5, that's going to give you a lot larger density than if you have a hot situation where you have 3 divided by 12. So as you increase your temperature, your volume will increase because your molecules or your atoms have a whole lot more kinetic energy. They're moving around a whole lot more. They're taking up more space. So you get expansion. And a larger denominator down here means that this value up here will be smaller. So as we increase the temperature, the density value is going down. And that makes sense when we look at the picture of air, okay, because we can see how the molecules or the atoms over here are farther apart, okay? So as you heat something up, the tendency is for it to become less dense. Now, that works with most things. So if we think of aluminum, the solid, if we heat it up, and I'll put the triangle over the arrow. Now the triangle, the delta symbol, usually means change, but when we put it over a reaction arrow, it means heat. Okay? So if we heat this up, what happens is we get liquid aluminum, and aluminum will melt above 660 degrees Celsius. And in the solid, the atoms are super close together and packed tightly. And then in the liquid, they're a little bit farther apart, and they can move past each other. They can slide past each other just fine. And so this right here is less dense, and this over here is more dense. So usually the solid form is more dense than the liquid form, and the gas form is the least dense. But water is an anomaly. So let's take a look at water. Now notice with water over here in this zone, as the temperature is increasing, the density is decreasing, just like it should. So look over here at this chart. So as we increase the temperature, look at that, going from 10 degrees Celsius to 100 degrees Celsius, we see that the density of water decreases, okay? So decreasing density, increasing temperature. Now the density of water is still about 1. Do you guys see the 0.99970, 0.99707, 0.95836? So right about here, it's gonna start to boil and become a whole lot less dense because we're forming gas there. But all the way along the line, our water is has the density of about 1. Okay, now it follows this trend until we get to a maximum density at 4 degrees Celsius, right there, of 0.99997. And then what water does is water says, oh, we're getting really cold as the temperature is decreasing. We want to set ourselves up to form ice, because it's going to form ice at what temperature? At 0 degrees Celsius or 32 degrees Fahrenheit. Okay, but other substances, when they form solids, their atoms or their molecules are packed super tight. They're closer together than in the liquid form. But water is a little bit different. If we look at this slide right here, we can see that liquid water molecules are pretty close, but when water molecules form their solid form, their ice, what they do is they arrange themselves into a perfect 3D crystal structure. And they're actually farther apart, those molecules in the solid form, than they are when they're in the liquid form. It just kind of puffs out. So that means that the molecules of water are actually taking up more room in the solid phase, which is different from other substances. So what happens is ice is less dense than water, because ice has a large denominator there. It has a larger volume because those molecules are puffing out in order to get that perfect 3D array. And you can see that here on this diagram, where the density actually decreases as the temperature goes down. Okay, so the density of solid water or ice right there at 0 degrees Celsius, it is 0.917, and that is less dense than the liquid water that has a density of 0.999 there, and that doesn't seem like much of a difference, but it does mean that ice does what? It floats on liquid water. So the solid version of water floats on the liquid version of water, which is completely opposite of what most substances do. Most substances, the solid version is more dense and it'll sink in the liquid version. So this crystal formation right here, which makes solid water or ice less dense than liquid water, is really, really good for life. This is a very happy situation for us. And the reason is when we live in a cold climate, which we don't here, but a lot of people do, what happens is that lakes and streams in the winter, they freeze over. So you get this layer of ice that forms on the top. And if the ice was more dense than the liquid water, it would do what? It would sink to the bottom of the lake. And then spring would come along, and instead of the warm weather melting the ice back into liquid, the heat from the sun could not get to the ice on the bottom of the lake, and the ice would stay there, and the next winter would come along, and you'd get another freeze, and that ice would sink, and then it wouldn't melt when the next spring or summer came along, and the same cycle would happen, and we'd end up as this big ball of ice. So it's really good for us that this happens, because then we get ice melting. And so, yay, chemistry! All right, that is the end of our density lesson. I will see you in the next video. Bye-bye.